This is Dr. Shankaraiah from Department of Physics. In earlier presentation, I have discussed about Module 1 crystal structures, and today I am going to cover a topic in Module 1 crystal structure, which is directions and planes in crystals. So we need to discuss about what is crystallographic directions, because we are going to discuss about directions and planes in crystals. Okay, so consider a cubic lattice as shown in figure. So this is cubic lattice. Okay, so this is a body-centered cubic lattice here. So we are just taking a cubic lattice. It can be simple cubic, body-centered cubic, or face-centered cubic. Okay, so I have considered this cubic unit cell as shown in figure. And the position of a lattice site is described by 3 coordinates, right? So we have said that this actually unit cell is a part of an infinite scheme, right? So we have a lattice, and unit cell is the smallest geometric unit. The repetition of this unit cell is going to generate a lattice or a crystal, right? That is the reason why now we have said that we can generate the lattice using this unit cell, and all these points are called lattice points or lattice sites, right? Now the position of each lattice site is described by 3 coordinates, because we have x-axis, this is x-axis, and this is y-axis, and this is z-axis, right? So the position of each lattice site is described by 3 coordinates, Cartesian coordinates, which are x, y, z, right, and which are expressed as 1, 2, 3. Okay. Yeah. So this is just reference. Sorry. So now these position of a lattice site is described by these 3 coordinates x, y, z, and these are expressed as x is equal to PA, and y is equal to QB, and z is equal to RC. Okay. So where A, B, C are lattice constants, I am defining ABC are actually axial lengths, or you can also call them as lattice constants, right? So ABC are lattice constant in x, y, z directions respectively, and PQ are integers, are rational ratios, nothing but you have integers in numerator and denominator. Okay, so ABC are lattice constant along XYZ directions, and PQR, these PQR are rational ratios, are integers. Okay, so the position of each lattice site in a cubic unit cell or in a unit cell can be described by 3 coordinates x, y, z, and these 3 coordinates are written as x equal to PA, and y is equal to QB, and z is equal to RC. Okay, so what is P? X is equal to P into A. What is P? P is a integer, and X is a axial length or lattice constant. What is Y? Y is equal to Q into B. What is Q? Q is a rational ratio or integer, and B is axial length or lattice constant. Z is equal to RC. What is R? R is again integer or rational ratios, and C is axial length or lattice constant. Now we can represent, or we can write down the position of each lattice site using PA, QB, and RC, right? Okay, so if the lattice constants ABC are taken as unit axial lengths, that means A equal to B equal to C equal to 1. Okay, so we are taking the lattice constants are axial length. So if I draw this crystal axis x, y, z, the axial length along x is A, which is unit, and B along y is B, along z is C, and all of them are of unit magnitude. So I am going to take them as A is equal to 1, B is equal to 1, and B is equal to C is equal to 1. So A is equal to B is equal to C is equal to 1. Unit axial lengths. Okay, now the coordinates of the lattice site will be, so what we have written it as so we said that each lattice point can be described by 3 coordinates x, y, z. And then we have written x, y, z as PA, QB, and RC. Okay, so then PA, QB, and RC. Then we said that we have defined A is equal to B is equal to C. I want to take simplest unit cell where A is equal to B is equal to C. All the axial lengths are same, unit magnitude. So then what it became? XYZ became P, Q, R, because A and B and C are 1. Okay, so now these are the indices of the lattice site. So now we can represent the position of a lattice site by this indices p comma q comma r. Okay, and are written within commas, separating the numbers and enclosed in parentheses. It's very important that the lattice site is denoted by the numbers p, q, r, where these p, q are separated by commas, because the representation is very important, because the direction of a plane is also given by integers, but it may be commas, may not be commas. So whenever you are representing the site, lattice site, you have to separate these pqr by commas and put them in parentheses. So if you write this like this in parenthesis p comma q comma r, that means it is a index, it is the index of a lattice site. Okay. So as an example, the indices of atomic sites in BCC cell are shown in earlier figure. Right. So in the earlier figure, if you look at the earlier figure, we have written the indices of the lattice sites. Okay. So I think we have given the lattice site indices for different atoms. So what is the lattice site of this atom? 0 comma 0 comma 1. So these pq are separated by commas and enclosed in parentheses, right? Because this is the index of this lattice site, that is the index of this lattice site, the index of this lattice site, this lattice site, this lattice site, and so on and so forth. This is at the body center, so it is 1 by 2 comma 1 by 2 comma 1 by 2. Okay, so these are the indices of the unit cell. And for example, let us take this lattice site. So this lattice site index is given as 0 comma 0 comma 1. Why is like that? So this is along z axis, the unit along z axis, the unit length is 1. So this is along the z axis, so x equal to 0 and y is equal to 0. That is why it is 0 comma 0 comma 1. Only along z axis it has unit length, it is 1. So p is equal to 0, q is equal to 0, and only r is equal to 1. Okay. For example, now take this. Take this. So this is a y plane. This is y axis and this is x axis. So this is in xy plane. In xy plane, so the along x axis, along y axis, you have unit length. So you have x, y. So this is xy plane. So that is why you have the length, unit length. So y is unit length and x is also unit length, but z you have 0. So x, y, and p equal to 1, q is equal to 1, and r is equal to 0. Similarly, y axis. So this is y axis. So x is 0, z is equal to 0. So 0 comma 1 comma 0. So this is x axis. So 1 comma 0 comma 0. Right. So this is a body centered atom. So all of them are off. So right, so 1 by 2 along x axis, 1 by 2 along y axis, and 1 by 2 along z axis. So that is the reason why the index of this body centered atom is 1 by 2 comma 1 by 2 comma 1 by 2. Okay, so somewhere we have another atom here, for example this atom, right? So for this atom, this is in xy plane. So this is y axis, this is x axis, right? So this is a xy plane. So this is in the xy plane you have at this point. Right. So along y-axis, so it has unit length. Along y-axis, it has unit length. So that is why y-axis you have 1. But along x-axis, if along x-axis, if you are at this point, it is 1. But if you are at you are in the middle. So that is the reason why p is 1 by 2. Right. So if you are here, p value is 1. But if you are at the center, from here to here, it is only half. From here to here, the length is half, and from here to here, another half. So that is why the lattice index of this lattice site is 1 by 2 along x-axis, 1 along y-axis, and along z-axis is 0. Okay. So this is how we can write the indices of lattice sites. Okay. So we have taken this body-centered cubic unit cell and we have written the indices of different lattice points. So the atom positions for the 8 corner atoms are 0 comma 0 comma 0, 1 comma 0 comma 0, 0 comma 1 comma. Okay, what are all these? These are all 8 corner atoms, right? So if you can draw this unit cell, so let me draw this. Okay, so let me draw this here. So I have to draw this unit cell, cubic unit cell, right? Cubic unit cell, A equal to B equal to C. So you have to be careful with that. A is equal to B. So you have all the squares. So this is 1 square and this is 1 square. And now I am going to join. Okay, so I have a cube, right? So yeah, right? So I have 1 corner here, 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 here, here. So 8 corners. So 8 corner indices of these 8 corner atoms is given by here. So the first, this is 0 comma. So this is, if I start from here, so this is 0 comma 0 comma 0. The index of if I consider this as x-axis and this as z-axis and this as y-axis, for example. So if this is x-axis, the index of this lattice site is, so along x-axis, so 1 comma 0 comma 0, and along y-axis this is 0 comma 1 comma 0, along z-axis, so this is 0 comma 0 comma 1. So similarly you can write all indices of all these atoms. Yeah, so 0 0 we have written, and 1 0 0 also we have done, and 0 1 0 we have done, and we have also done 0 comma 0 comma 1. So all these other atoms like 1 comma 1 comma 1, so 1 comma 1 comma 1 will come yeah, so, and 1 comma 1 comma 0, so that is xy plane, so that is here, so this is x and this is y, so this is 1 comma 1 comma 0, right? And what about this we have written, and what about this? So this is yeah, so this is along z-axis, so this is z, and yeah, so this is actually 1 comma 1 comma 1, okay, and this is z and xz plane, so that is 1 comma 0 comma 1, 1 comma 0 comma 1, that one is this, and 1 comma 1 comma 1 is this, and 0 comma so this one is what, this is y and z, yz plane, so that is 0 comma 1 comma 1, 0 comma 1 comma 1 is here. So only one is remaining. Where is that one? So that is 1 comma 1 comma 0, 1 comma 1 comma 0 is where? So we have written somewhere 1 comma 1 comma 0, right? So yeah, 1 comma 1 comma 0 is also done. 1 2 3 4 5 6 7 8, 1 2 1 2 3 4 5 6 7 8. All the 8 indices of all 8 corner atoms we have written. We are able to write the indices of these all 8 corners atoms of the cubic unit cell. Okay, so if you take body center atom, so that will be 1 by 2 comma 1 by 2 comma 1 by 2, because it is half of the length along x y z direction. Okay, because we have taken unity axial length, so a equal to b equal to c equal to 1. Body centered atom is in the middle of along, so a is equal to 1 by 2, b is equal to 1 by 2, and c is equal to 1 by 2. So if we are taking a equal to b equal to c equal to 1, so that is p equal to 1 by 2, q is equal to 1 by 2, and r is equal to 1 by 2. So the body center atom is 1 by 2 comma 1 by 2 comma 1 by 2. Yeah, so that is what is given here. Okay, so this body center atom is 1 by 2 comma 1 by 2 comma 1 by 2. So the minimum number of coordinate sets necessary to specify the locations of all atoms in a unit cell are equal to the value of z. So the effective number of atoms per unit cell. So if you want to find out all the number of indices of indices of the lattice site, the minimum number of coordinate sets we require is equal to the effective number of atoms per unit cell, so that is z. So for a simple cubic unit cell, if you want to write all the indices of the atoms, so you need at least one coordinate set. For a BCC you need 2, and for FCC you need at least 4. So many crystals exhibit properties that are dependent on the direction. Okay, so in the which they are measured and on the direction of the external stimuli, such as the electric field, magnetic field, or mechanical stress acting on the crystal. So why do we need to study about the directions? So to understand that, we need to calculate, we need to look at the directions, because you can apply external stimulus. For example, you want to apply electric field and look at the properties of the crystals. So you have to know along which direction I am applying the electric field. Or if you want to apply magnetic field to a certain crystals, and you look at the properties, you want to look at the phase transitions and how the crystal is changing, different properties, mechanical properties, and so on and so forth. So whatever external stimulus you are applying, you should know along which direction I am applying, and what is happening in a crystal in different other directions, or along the same direction in which I have applied the external stimulus. Okay, so it is important to know the directions in a crystal, because we can apply external stimulus and look at the changes various changes in a crystal on application of external stimulus such as electric field, magnetic field, or stress, which is a pressure. Okay, so therefore it is essential that we know the reference directions in crystal. That is why it is important to know the directions of crystals. So to describe a direction in a crystal lattice, a straight line passing through the origin is chosen. First, if you want to know the direction in a crystal, you need to, a straight line passing through the origin is chosen. First, you need to draw a straight line that is passing through the origin. And the coordinates of the first lattice point lying on this line are utilized to denote the direction of the line. Okay. So first you need to draw, to understand or to know the direction in a crystal. First you draw a straight line going through the origin, and along this straight line look at the first coordinate set of the lattice point, and that coordinate set is used to find out the direction of this straight line which we have drawn. Okay. Thus the indices of direction are the vector components of the direction resolved along each of the axes and reduced to the smallest integers. So the vector components are multiples of lattice constants. Okay, so we will know this about this clearly as we go on, right? So indices of direction, whatever we are going to write the direction, so we are writing some integers to denote the direction. That direction is resolved along the axis and reduced to smallest integers. So we will know how to write down these directions, right? Okay, if the direction passes through the origin, then the indices of the lattice will also be the indices of the direction. Okay, if the direction is going through the origin, then the direction of the indices direction will also be the indices of the lattice. Okay, so the indices of the direction are calculated by the following procedure. So how do we write the indices? We have calculated, or we have known, now we have understood how to write the indices of a lattice site or lattice point. Now we need to know the indices of a direction in a crystal or in a lattice. So how to do that? Okay, the procedure is this. It has some step. The first step is, first find out the coordinates of the lattice site nearest to the origin in a given direction. So in any chosen direction, first write the coordinate of the lattice site. First write the coordinates of the lattice site nearest to the origin in a given or in a chosen direction. Whatever direction you choose, first you choose a direction, and in that direction look at the first lattice, nearest lattice site, and for that lattice site write the direction coordinates or indices of the lattice site that we have calculated in the previous slides, right? That is the first step. The second step is, the coordinates are then divided by appropriate unit translations. So whatever coordinates you have written, those coordinates are divided by appropriate unit translations. So we have to divide them by unit translations. So that is the second step. Third step is, if fractions are obtained, when you divide these coordinates by unit translation, if you get any fraction, okay, each fraction is multiplied by the smallest common divisor, right? So this is the third step. The fourth step is, the integers are obtained are indices of direction written in square brackets. Okay, so this square brackets, so the P, Q, R without commas and they are enclosed in square brackets will tell us about the direction of a direction in a crystal. Okay, square brackets enclosed in square brackets, P, Q, R without comma. So this will tell us the index of a direction. Okay, so thus the indices of direction in a crystal are the set of smallest integers which have the same ratios as the components of a vector in the desired direction referred to the axis. So these are the 4 steps to find out the direction of in a crystal. Okay, what are the 4 steps? Again, to revise, first write down the coordinates or index of a lattice site nearest the origin. Once you write the coordinates or index of a lattice site, divide by the unit translation. Once you divide by the unit translation, if you get any fraction, multiply it with the smallest common divisor. Okay, then when you multiply with the smallest common divisor, you are going to get integers, and write the integers in square brackets without comma. So that will tell you the direction of a direction in a crystal. Index of a direction in a crystal. So that will tell you the index of a direction in a crystal. Okay. So as an example, let us consider a cubic unit cell shown in figure. Okay, so I have taken a cubic unit cell here. Let the O be the origin. So this is the origin point. O be the origin, and the point P is at the position 0, B 0. Okay. So now we are taking some point P. Where is the point P? So yeah, P is here. So this is the point I have taken. P is at 0, B 0. Why I have said 0, B 0? So this is y-axis. The length along y-axis, axial length or lattice constant is B. Along z-axis it is C, and along x-axis it is A. Axial lengths A, B, C are the lattice constant along x, y, z directions. Okay, so this point is here. So the length, axial length is 1. So that is why I have written this as 0, 1, 0. So this is the index of this. This is the index of this OP. So if I want to draw this in this direction, the index of this direction is 0, 1, 0 enclosed in square brackets. Okay. Okay. So how did I get 0, 1, 0? First, I have to choose the first. Okay, in this direction, if I want to write the index of this direction, first I have to choose the lattice point. So this is the lattice point. So the lattice point, the index of this lattice site is 0 y-axis. So 0 comma 1, 0 comma b comma 0, right? So I am going to divide by the unit translation. So I will get 0 comma 1 comma 0. 0 comma 1 comma 0. There are no fractions. If I need to write them in square brackets without comma, 0, 0, 1, 0 in square brackets. So this is the index of a direction. Okay. So therefore the indices of point P are yeah, as I mentioned, 0 comma 1 comma 0 in parenthesis. The direction of OP is given as 0, 1, 0. Okay. On the other hand, the direction of PO is specified as 0, 1 bar 0. Okay, it's important. So we have calculated, we have looked at the index, or we have find out the index of this direction, right? So the index of this direction OP, this direction is 0, 1, 0. Now I want to look at the direction, this direction PO. The index of this direction is 0, 1 bar. Okay, 0, 1 bar 0. 0, 1 bar 0. The bar on 1 is represent the negative direction. You are going OP is the positive direction. Now you are going into PO. So that is in the reverse direction, or it is in the negative direction. That is why I am going to put 1 bar only on bar on 1, because it is along y-axis only. Same, but it is negative, reverse direction. So that is why 0, 1, 0. Now I am going in the reverse direction, 0, 1 bar 0. So the bar on 1 will, in this case, will tell us the negative direction. Okay, so here we have just calculated the indices of a one particular direction in cubic unit cell. Similarly, the directions of OQ and O are indicated as 1, 0, 0, 0, 0, 1 respectively. Okay, so OP, so this direction we have written. Now you can even write the direction of OQ and OR. For example, OR, right? So I want to look at this direction. So this direction, the nearest lattice site is this, and the index of this lattice site is 0. So this is z-axis, right? 0, 0, C, or I can write it directly by dividing. It will become 0, 0, 1 unit translation, right? So 0, 0, 1, and now I got this. If there are no fractions, if there are any fraction, I need to multiply the least common divisor, but no fractions. So I'm just going to write them in square bracket 0, 0, 1. So the 0, 0, 1 is the index of this direction OR, right? So OR direction is 0, 0, 1. Very good. So now we want to write the index of this direction OQ. So in this direction, the nearest lattice site is Q, and this one is along x-axis. So 1 comma, actually you should write A comma 0 comma 0. We are going to divide by the unit translation A. So that is 1 comma 0 comma 0. No fraction, so no multiplication. So that is 1, 0, 0 of OQ. So OQ is 1, 0, 0. Okay, so we have calculated the indices of directions in this lattice. Okay, the direction of OS may be determined as follows. Okay, there is one more. So this is what we want. So we have looked at these three: OP, OR, and OQ. Now we want to calculate OS. So this direction we want to calculate. So how to calculate the direction of OS? So the direction of OS may be determined. Okay, so the positions of indices of the point S are Okay, so this point, index of this point we can write. So this point is in the center of xy plane. So xy plane in the center. So this is off. This is 1, so it is in the center, and this is 1, but it is in the center, so that is xy plane. So 1 by 2 comma 1 by 2 comma 0. Okay, so then using instruction 3, if there are any fractions obtained, multiply with the small divisor. The direction of line OS is obtained as, so we have 1 by 2, 1 by 2, so you need to multiply it with 2. So multiply with 2. So first we have 1 by 2 comma 1 by 2 comma 0. So this is OS direction. We want to write the direction, index of this direction OS. So that is first we are going to write the index of the lattice side, that is 1 by 2 comma 1 by 2 comma 0. So then if there are any fractions, we need to multiply with the least common divisor. So that is, we need to multiply with 2 into 1 by 2 comma 2 into 1 by 2 comma 2 into 0. So that is 0. So that is 1 comma. Now we are going to write the index of a direction. So that is 1 1 0. So this is the index of this OS, direction OS. Okay. So we have learned how to write the indices of lattice point, and that are used to write the indices of direction in crystal. So all parallel directions have the same direction indices as shown in figure, and the parallel directions are equivalent. So this, for example, this and this are parallel. So you can write the same indices, 1 comma 1 comma 0 and 1 comma. So all the parallel directions have the same indices. This is very important point, right? So PQR represent the family of directions. Suppose if you find anything represented in angular brackets 1 1 0 or something, right? So this will tell us our 1 0 0. For example, 1 0 0 in angular brackets. So integers enclosed in angular brackets tells us about the family of directions. Okay, so these 1 0 0 enclosed in angular brackets, you can write them as 0 1 0 0 0 1 1 0 0 0 1 bar 0 0 0 1 bar 1 bar 0 0. So there are actually 8 directions. So indices of 8 directions, and you can group them together in a simple as angular brackets 1 0 0. Okay, so this one is going to change its place, 1 0 0 0 1 0 0 0 1 1 bar 0 0 0 1 bar 0 0 0 1 bar. So it will give you indices of 6 directions in a crystal. Okay, so yeah, I think I am going to close it here, and in the next presentation I am going to discuss about lattice planes and Miller indices, and yeah. So to summarize, we have learnt how to write the indices of a lattice site, and how to write the indices of a direction in a crystal. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.